Namhoon, thank you for this nice introduction. Right, you were very nice to me, and yeah, also thank you for the invitation, and of course also thank you for all of you making time to come here. I know your research is currently not going further, and you're making a break. So thank you for being here and listening to me. Yeah. So the title, Safety Guarantees for Aerospace Systems, a control barrier function perspective. As Namhoon told me, some of you are working with control barrier functions, right? I hope I will not bore you throughout the presentation, right? I will try to provide certain interesting results and notions that are maybe helpful for you or at least interesting. And also for the ones who are not familiar with control barrier functions, I'll try to give you a small introduction to the topic. I think the mechanism is not too complicated, right? So everyone with a control background should be hopefully able to understand the mechanism in some slides. Yeah, safety, just as a heads up, I know it's a very odd word, right? Because in aerospace, every controller should be safe, right? So the term is basically coming from the control theory community who's saying safety is equal to state constraint, right? So every time when you hear safe or a safe controller, it's basically just the safe constraint, state constraint so controller, right? So just keep this in mind. The motivation for such state constraint controller is actually, yeah, just obvious, I guess, right? We have a lot of systems that are state constrained. Maybe for you guys, the most interesting one is on the left side is an example from the Ministry of National Defense from South Korea, right? Where they made very nice demonstration on, yeah. It's not shared in the Zoom. Okay, just give me a second. We're back on track. Yes. Yeah, excellent. So yeah, so this is a very nice demonstration of your swarms, right? And what you're trying to do is you would like to use the swarm such that each of the drones are having some sort of task they are trying to accomplish, and based on that, each of the drone will provide or generate a trajectory that it follows. But what you need to ensure is that those drones are not colliding with each other, right? So it's a very complex task. Very nice demonstration from here. But you have other examples as well, right? You have here a hypersonic system. It's a scramjet, and those scramjets are very sensitive towards angle of attack. Let's say magnitudes, right? So what you need to ensure is that the system will stay in a certain angle of attack band. Otherwise, you will have the problem of inlet unstart, right? So this is also a nice example. Of course, you have satellites which are on their orbits, and when you have space debris or other satellites, and the satellite will collide, you have an issue. Fighter jets with structural load limits, stall limit, etc., or this very nice snake-like roboter from the University of Tokyo, which is trying to creep up its way over there, and it tries to prevent colliding with the surroundings. And also that's an example where you could use control barrier functions, right? So yeah, multiple applications or fields of applications for the method. However, yet, is it working? Yeah, yet we don't know how it works. So some of you do, others don't maybe. So what I will do is in the first part of the presentation, I will try to highlight the concept and the mechanism of control barrier functions. And from there on, I will show that, let's say the vanilla version, right? The basic version is not as easy to use in reality as we think it is. And there are certain challenges which need to be addressed. And I try to highlight some of the challenges and also show some of the results we obtained in the last years. And from there on, I'll make an outlook and conclusion. So in order to make a system safe, we first have to evaluate if the system is safe, right? So we need a metric that allows us to evaluate the safety of the system, right? And in the first step, we just look on a very simple nonlinear continuous system. No control input, we can just observe it, right? And by observing it, we can evaluate if it's safe or not. And if we do that, it's called safety certificate, right? Because we don't control it actively, we're just looking into the system. And what we actually would like to obtain as a behavior is that for a system for which we have like a model, right? And the model, it's maybe valid for a set of states, which call it Xi, right? You get an aircraft model with a large data set, right? But we know the system can only be used in a certain constraint set, right? And this constraint set is the safe set. So this is actually the operational flight envelope for an aircraft, right? And what we trying to ensure is that the system always stay in this operational flight envelope, or say ZS. And in order to evaluate this, we are searching for a continuously differentiable function h, and it's this here. And h has some nice properties. It's, as you can see here, always greater or equal to 0, right? As long as we are in the safe set comfortably, it's strictly positive. And if we are in the boundary, it's 0. So it has some notion very similar to the Lyapunov functions, right? But it's easily to construct such function, or at least a candidate, right? And from there on, we can use this as evaluation point to see if the system is safe. But we also, if we have such function, we not only can just see on the value if it's safe currently, we can also evaluate the conditions that are needed that this in order to ensure that the system stays forward invariant, right? And forward invariance means once we are started in a safe set, we will always stay in the safe set for the whole time, right? And the condition is very simple. It's just the h dot at the boundary of the safe set needs to be greater or equal to 0, right? Because the function needs to be always positive or greater or equal to 0. We need to make sure that it doesn't slip down, let's say, the value. But this will only give us a condition on the boundary, right? And if we would just use this, we will maybe end up with some uncontinuous bang-bang-like safety filter or safety approach. So we need something smoother, and some folks, I think the first one is debatable, right? There were like some research in the early 2000s, and I think the first one who ever come up with a similar idea as Ames in 2014 was Frank Algova, and one of his PhD students who came up with this formulation. And the idea is to just say we generalize this very strict Nagelmus invariance principle to all locations within the safe set, right? So as you can see here, we still have this inequality kind of approach, but now we have this the function here instead of just the 0. And by doing this and making this function basically a function of the position within the safe set, we can generalize this to be used over the whole safe set, right? So, and the idea is very simple. If you just look into this, we look again, this is the inequality, and basically we are searching for a lower bound on h dot, right? We're just saying, okay, hey, based on where you are, we're giving you a lower bound on the slope. And the most popular approach is to just use a scalar parameter gamma times the value of the CBF value, right? And this is basically just an exponential lower bound. So we're just saying, okay, by doing this, we have an exponential lower bound when we approach the boundary of the safe set. And as long as our H dot of the system is above this line, we're good to go, right? And interestingly, or also a very nice property of this approach is that by choosing gamma, we can actually define how we approach the boundary, right? So if you, this is for a first order system, but if you choose a gamma that is very high, you research for an exponential function that goes very close to this direction, right? And the further you go in this direction, it means your safety constraint becomes active later, or very close to the boundary, right? So this has some implication on your actuators. You have control input limits, but it also make your safety filter less conservative, right? The lower you get, the higher it gets like this, and this means you will start to intervene earlier down the line, right? So yeah, so whenever you are trying to figure out or tune your CBF, you can always tune this parameter and change the system, change the behavior, how the system is rendered safe. How the system is rendered safe is a very good keyword, because until now we just looked at certificates, right? We had no control inputs. Now we can just extend the nonlinear system we had before in a very simple way. So we have now a control affine system, as you can see here. And what we just need to make sure is that your system somehow is always in line with this constraint here, right? And this there is nothing else but your H dot. So it's the same thing as we had before, but now we have just U additionally. And by that, we can actually obtain, depending on the problem, some constraint on U, right? Either a lower bound or upper bound, depending on the problem. But we can just say, okay, wait, if we know our U needs to be something like this, and then the system is considered to be safe, right? And this can be actively used in a control setting, meaning imagine you have your performance-oriented controller, right? Something you just use, right? You want to track a reference, you want to stabilize the system, and you just design it. But you're not able to design it with respect to so-called safety, right? For example, you have a UAV, you can't add, let's say, pillars for objects in your control synthesis, right? It makes no sense. So you have to neglect it, and you just look onto some robust stability or reference tech and performance. But what eventually will happen if you don't have a safety filter is that your system will collide, right? Here's like just a simple pillar. The system will fly against this pillar. But if you just extend it with a so-called safety filter, right? Give me a second. Does it work? Okay, we'll switch over to this. If you just switch over to a safety filter, and first of all, you have the same constraint I just showed you before, right? So this is something, it has to be always given. So this is the point where you evaluate the system. But I will show also later, it will give you a solution space, right? It's basically a bound, one-sided bound on U, meaning you have multiple solutions which will respect this constraint. So therefore, you search for a solution that is as close as possible to something, and this something is your nominal controller, your performance-oriented controller, right? Because you would like to keep as much performance as possible in the system while being safe. And this is what this cost function is giving you, and it's basically balancing, right? And if you do it like this, you can obtain somehow of like this behavior where the system is able to getting to the goal by minimally less, or let's say minimal invasively trying to avoid those pillars, right? This is a very simple example, but you will see when you're, for those who ever worked with CBFs and for those who will work, you can come up with something like this in a very fast way, right? So it's like very helpful. I think this is also why control barrier functions became so popular, because they can address very complex problems in a somehow easy way, I would say, right? Of course, it gets more complicated if you dive into the topic and you find the real world problems, but the vanilla version, the basic version is very straightforward. Something you have to consider is, I just showed you the straight approach to control barrier functions, right? You just have your model, you can make the first time derivative to get h dot and everything is fine. But it's just just a partial truth to it, because you will have sometimes the issue that you make the time derivative of your system or the dynamics you're trying to control, and this part, or basically just the part where U is acting on 0, right? It may somehow, you could argue, it means you don't have any controllability on your safety at that point, right? You can't render the system safe with the control inputs you have available. And the classical way of dealing with that is very let's say known case of nonlinear control, because you will have something similar to NDI or backstepping, is to make another time derivative, right? And you come up with the recursive way of deriving control barrier functions, and this way is called, or this method is called higher order control barrier HOCBFs, right? So you would just basically, you continue to make the time derivative and hope that at one point your control input pops up, right? And if you have that, you're good to go. And with that, yeah, and you just use this final inequality constraint, right? Instead of the one we had before, and you can in your safety filter, and it works quite good. And yeah, with that, you can actually already start to render aerospace systems safe, right? So this is a very simple missile dynamic system. We have the nonlinear dynamics, and what we're trying to achieve is that the system will stay in a certain flight envelope, right? You have stall constraints, you have load constraints, and you need to make sure that the system stays safe. However, it's a missile, right? You have some sort of PNG law that is trying to intercept with another missile. And for this PNG law, you have no guarantees that the loads that are commanded, or the NZ command that are commanded, are staying within a certain range, right? So you could use control barrier function to constrain the system in a certain domain. And in this case, a very classical NDI controller is used, just a cascaded NDI controller, very simple, just straightforward, getting you your control inputs. And you can retrospectively design a control barrier function, or let's say a safety filter, to ensure that the system stays in the flight envelope. And the idea is to pop this CBF-based safety filter right after your NDI controller, and derive the condition. What you're trying to do is, in this simple case, I just said, okay, you can go for an upper bound in alpha. You can basically recompute all the load limits into alpha constraints, right? And it just makes stuff easier. And this is the candidate to ensure this, right? And in order to construct this CBF, you look into this first constraint, and then you make the assumption that alpha max is constant or piecewise constant. And by that, the time derivative on this is 0, right? And this helps you because now you get your second time derivative and you obtain something like this, right? And it's very simple. Again, this is the way of doing control or higher order control barrier functions, right? It's always like the time derivative of the one before it plus some parameter times this function, right? It's straightforward and you come up with something like this. And then you look again, is my delta popping up somewhere there? And if not, you make another time derivative of this. And then you see that your delta is somehow in this function here, right? I didn't put it here because it's too much, but alpha dot dot is basically proportional or directly correlated to q dot, right? And q dot is somehow your moment, and the moment is directly somehow connected with your delta, let's say the pitch command you give, right? So then you have your final CBF that you can use. And if you use it, it's like working if you have the right model, right? It's another question. If you have the right model, you can see that basically more or less all of your CBF tuning stuff will work. So in this case, for the HOCBF, what you see is you will have the constraint, and the constraint you have two free parameters, right? Gamma 1, gamma 2. And here in this case, I just try to show that no matter how much you change them, as long as they don't violate your input constraints, all of them are valid. But they will change how the system is rendered. Say, if you go for, let's say, more conservative setting, you see the intervention to get to the limit is, let's say, more conservative, right? Here's the red line is the limit here, and this is what has been commanded to the system. And if you're going for more, let's say, challenging or performative setting, you will see that it will go steeper, but at the same time, by doing that, you will see alpha dot in the meantime goes quite high. And in order to cope with that, the system has to go for bigger control inputs. And in order to generate the bigger control inputs, you will maybe end up with the case where you at one point violate the rate constraint, right? And as like control engineers, you always have to have in mind, okay, every design choice has implications down the line. And in order to find the right design choice, you need to look like on different places, right? And if you do it, it works. If not, maybe, I don't know, right? And this is a small introduction to control barrier functions, right? I hope it was helpful for those who are not familiar with the topic. Of course. Oh, yeah, please always. Yeah, also in general, if you have questions, please just, yeah, dive in. Yeah. 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 Yes.
So you were saying that.
Yeah. It could work, but again, it's like something I just thought about it, just make small tests, right? But yeah, would need much more research on this in order to make like qualified yeah answers or to give qualified answers to the topic. Yeah. Yeah. Yeah, exactly. Yeah. Mhm. Yeah.
Saying what you said. Well,
Yeah. Again, I'm not. It's like still something I have to evaluate because I just did it, and I think, but maybe like to, um, uh, like to include all of you. We had a very nice discussion yesterday, right? And we had I talked about something that is it was quite interesting to me because it's somehow not in line with the theory, right? Um, you see alpha dot here, right? And alpha dot has this term CZ delta, right? So there is already a delta term in alpha dot, but I still comfortably, right, or let's say comfortable, but with confidence said that I did something with alpha dot dot, right? And alpha dot dot is function of q dot, and there is your term cm delta delta, right? And back then I did it because I was, and it works, but I did it more or less just by the fact that I was so used to NDI, right? And in NDI, you normally neglect this bit because it's an unstable zero, right? And if you invert this, your controller will blow up, right? And I did never question it. And when I derived the CBF, I just saw that and I was just like, yeah, I'll just neglect that. I know it's bad. But when I thought about it with some time, I questioned myself, okay, why can't this be directly used, right? And actually it works, right? You can do that, but there was still some sort of question because it makes no sense to me. But maybe it makes sense to you, so please give your input. So from my impression, right, when you look from a physical perspective on non-minimum phase behavior, right? You will find some issues from a theoretic perspective, such that if you would use directly this as your CBF, right, or as part of your CBF, you will treat this as an internal dynamic, right? And the problem is that this internal dynamic is counteracting this level of control that you're using, right? Your see that delta, which would generate, let's say, a lift in order to respect your load limits, generate a lift that is counteracting the lift direction of the vehicle, right? Normally you would try to make a negative lift to create a moment, to create a positive lift, right? And if you do it like this, you would start to make negative lift in order to keep the load limits low. But at the same time, you will introduce a moment which will try to work against it. And this is something that is not included in the CBF. So you will get some awkward behavior, I was assuming. But I didn't saw that in the simulation. And I just discussed it or brought this to Namhoon's attention, that this is like something that should be maybe investigated, because it's like, yeah, not really understandable from my side right now, right? But maybe I also made the mistake in the simulation, so maybe it should be further looked into. But yeah, I was able to address the point, right? So hopefully it was not clear. I think yesterday. Yeah, yeah, yeah. But yeah, so again, if you ever have time to look into this, please feel free and give me feedback how it worked out. Um, right. So this was an open question, but there are still many open questions in control variable functions. Um, if you're just placing the safety filter right behind your controller, you have immediately one big problem, right? If you're having your controller that is trying to track a reference, and then have a safety filter here, in most cases, these controllers, they have integrators, right? You have a PI, maybe PID, I don't know. And it tries to force following the reference. When you put a safety filter just right behind it, right? Your integrators will wind up, right? Because they will try to force the system to follow the reference because it has no idea that the safety filter is not allowing that, right? So in order to cope with that, you would need like anti-wind-up schemes to ensure stability of the system, right? Otherwise, you will have issues. Another problem is that you will have issues with your robustness guarantees. I think we talked about it with also like just in the meetings before. If you have the safety filter placed, or let's say like this, normally in aerospace, especially in aerospace, when you design a controller, you always have to make sure that you have certain phase margins, certain gain margins, right? Otherwise, you are not able to certify your controller. And those things are normally done just for your LTI, closed loop system, on a certain operating point. If you place a safety filter right behind it, it will adjust your input from the controller, right? And if it adjusts the input of the controller, it will shift the pull location of your closed loop system, right? And if the safety filter is not designed such that those poles are constrained to a certain region or analyzed with respect to that, you maybe become very unstable, right? Or let's say, maybe not unstable, but marginally stable. The phase and gain margins are getting very low. And basically, if you have active constraints and have uncertainties at the same time, you could get problems, right? So also in the synthesis of CBFs, always keep this in mind, right? We have some new results I didn't include in the presentation, but if you're interested in that, happy to discuss this. Yeah, other than those problems, which are, again, very critical and still yet not fully addressed, there are some design challenges on which we had some results. So this is like something that is always relevant, real-time capability, right? So you have the optimizations acting on the often like lower level of your controllers. And if they are not real-time capable, you will not make it. Sometimes you have over-actuation and input limits, especially for like, I don't know, those newer systems, VTOL controller systems or quadcopters, hexacopters, etc. Model environmental uncertainties and efficiency in multi-agent scenarios. And I'll just try to go topic by topic through it. Again, I'll try to be some sort of high level in order to not lose all of you. But maybe not as detailed as someone would like to have it. So when you have questions, feel free to ask questions, okay? So the first topic is input limits and over-activation. And the motivations, mostly these kind of systems, right? UAVs, VTOL systems, etc. And for some of them, we normally, I think the easiest way is to look into the control problem from a feedback linearization point of view, right? And normally you try to bring the system into like some sort of like feedback linearized input-output relationship, right? Where you try to control the system with respect to a virtual input, and you obtain somehow like a control effectiveness matrix B. And in order to control the system properly, you would have to use this control law. And for this control law, we would have to invert B, right? And this is like more or less always the case for NDI, right? You have to make the inversion of your control effectiveness matrix for a control IFN system, right? But if B is not quadratic, right? If it's like let's say over-actuated system with a rectangular B matrix, then you have no inversion, right? Normally what people do is they interpret the problem as an let's say some sort of like a search problem, right? Because if you're overactuated, your mathematical problems underdetermined, right? So you have multiple solutions to the problem. And the researchers and engineers came up with something called control allocation, where they basically search for a proper solution by using convex optimization, right? So this is just saying, okay, hey, I know there is the desired virtual input, could be a moment, right? And I know this should be equal to this in your hope, right? So I'm searching for a solution that minimizes the Euclidean norm between them, right? And if you're very good, this becomes 0, right? And then you have the minimum. If not, you're searching for the closest one while respecting your input constraints, right? And this is how control allocation works. If you're neglecting your input constraints and make this to an equality constraint here, you get something called like a pseudo-inverse, like Moore-Penrose pseudo-inverse. So, but this is like the one that is the formulation that's respecting your input constraints. And if you are look into this, you will see that this is basically a very similar problem set as you have for control barrier functions, right? And if you have then the problem that you have an overactuated system, while you have safety constraints, you will end up have to combine both of them, right? So you have then a combined problem. And in order to give you like an idea of this, I have like this very small problem. Basically, the motivation for that was like a hypersonic light vehicle, right? Which has flaps on the upper side and on the lower side, but I just abstracted this to something like this. I don't know. And you have like linear dynamics, but the properties are very similar. And for this system, you're trying to obtain tau des of 1, while you have U1 and U2, so you have more control inputs as you as degrees of freedom to control. This is the optimization problem I just showed. And additionally to the control inputs, control input limits, you also have now the safety constraint, right? And this is something we're trying to solve. The task is therefore we are searching for something that is in line with this, right? So we try to follow or find a solution to tau des or tau desired equals to 1, while the system stays in certain limits, and the certain limits is somehow like, let's say, an angle of attack constraint or an attitude constraint on this axis, right? And just in one direction gives us this CBF candidate. And if you implement everything of this, you will see how the mathematical problem is set, and also how the constraints are interacting with each other, which is quite interesting, or at least it was for me. So if you have in a 2D case, right? If you're having a tau or a moment command on one axis, what you actually obtain is this magenta line, right? And this magenta line is a line which provides on which all the solutions for the commanded moment are laying on, right? So any point on this line will solve your problem. But again, you have the cost function, right? And you try to minimize the cost function. So normally, if possible, you search for a solution which is right here on the center 0, right? But you normally are not able you're not able to find such solution without any constraints. We have the inequality constraints. So the box constraints, the input constraints will give you a box. This is this box, right? And the CBF constraint will give you this region here, the red region. So, and this is what I've meant before about the solution space. Basically, everything on this side here is safe. Everything on that side is unsafe. And for the box constraint of the input is everything in this box, right? And normally you're trying to search for a solution that is outside of the red region and inside of the box, and also laying on this line, right? And in this case, it works because no constraint is active, right? So we're good to go. If we have active input constraint, the magenta line is laying outside of the box, right? So now we have to search for a point on the magenta line that is as close as possible with respect to the box. So you just look and see, okay, the box, which is the available admissible set of inputs, has this edge here, and this edge is the closest to the magenta line. So we go with this, right? And at the same time, you need to make sure that your safety filter constraint is also outside of the solution. When you have an active safety constraint, it's the same on the other side, right? So now we have the magenta line, and the full magenta line is on the red side, right? Unsafe. But this part is in the admissible set of inputs, but again, unsafe. So what you now search for is the closest point on this boundary, right? Which is the boundary of the safety filter or the safe set, which is as close as possible to the magenta line, right? And if you do this, I think you get a very nice feeling of what the optimization will basically search for and do. And of course, sometimes you have the problem that you have active input constraints and active safety constraints, right? And then you need to search for a solution that is somewhere here, right? Well, it's one solution, right? It's not the solution. It's not optimal in any sense, but at least it's not in violation with your constraints. And yeah, so this is what the optimization is doing, right? And as you can see here in 2D, it's a very nice geometric intuition behind it, but it grows, the complexity grows with degrees of freedom, right? And this is like what we saw in the control allocation problem, that when you combine then you just construct the safety like QP with all the constraints, that of course you get very good solutions, but the complexity increases, right? And if you have a lot of control inputs, right? If you have like, I don't know, a system with 50, 60 input variables and also a lot of safety constraints, you will get an issue. And maybe there are like other ways to look into the problem. One problem is to just go back to the vanilla version of safety filter, or let's say the most obvious one, that you're just saying, okay, I know my safety filter should be designed on your control input level. And I have a control allocation algorithm like the pseudo inverse or QP that is solving my problem separately already, and it works quite well. I just place a safety filter right behind it and call it a day, right? And this works quite okay, but has some issues. And the issues is that if you're over-actuated and you have potentially a large vector of control inputs, you will have the problem to consider this large input vector on your safety problems, right? And if you have also multiple safety constraints, the problem becomes quite difficult to solve or to be solved. And also the problem is that sometimes you would need to let go or to weight some inputs or actuators in a certain way, and it's getting difficult on this level, right? And therefore we just looked into doing it on the pseudo control level, right? So on the virtual control input is rendered safe. It works quite well, and it also has the benefit of lower dimension, right? Because you just basically have just 3 degrees of freedom, right? Which you control maximum, maybe 6, I don't know. But it's still way less than your input constraints in most cases, or input vectors or inputs actuators, and therefore easier to solve. But you have the problem that you have to abstract your input constraints into this level, which is fine, it works, but it has to be addressed somehow. But therefore we thought, okay, maybe this is a potentially best approach. And therefore we implemented a safety filter on this pseudo control level. And then afterwards used the QP to render, to control allocate, or to make the control allocation. And actually, when you look into the problem in more detail, you will see that the problem I just saw before, right, with the inequality constraints can be further simplified to just simple box constraints on your pseudo control level, right, which is easier to solve. The other one is not that simple. And if you go further down the line and you have some condition met, you can actually decouple the different degrees of freedom, right? So you could, for example, for an aircraft, you can decouple roll safety from pitch safety from yaw safety. And if you do this, you will end up with saturation blocks. So there is no optimization needed anymore. So that is cool, and you definitely save some computation time with that. And this is what we've done for like a hexacopter. So the lead on that was Simon from TUM, and he implemented this to like a hexacopter system, as you can see here. And we compared also the different settings I just introduced, right? So this is the one we propose, right? Before, because we have the safety filter before the control location. This is the integrated one where you have both of them together in one optimization. And this is the one where you do the control location, the safety filter after the control location, right? And as you can just see, by just placing the stuff before and after, you will drastically reduce the computation time. So this is quite good. And also you see that on, at least interestingly for the max, the integrated one was the lowest, the slowest one. But the mean was for that not as high as for the one afterwards. To be fair, I don't know why, but it's just like that. But all of them were able to provide safety, right? So this is also interesting. So all of the settings work, but some of them have some benefits or not, and it's always an engineering question is how you choose your architecture. Right. Any questions to that? No? Okay, that's good. Then we can dive into the more, for me personally, more interesting field. Model and environmental uncertainties. Yeah, so the CBF systems that I just showed before just assume that the model is correct, right? But this is not the case. And if you don't have a correct model, all the nice guarantees you just obtained from your computation are not valid anymore, right? So you can't use them. And in aerospace, at least, we have multiple issues with uncertainties. Of course, we have like uncertainties for systems that are newly developed, right? And we can't trust purely just CFD, so we need to make applied experiments, system identification, etc. But even if we do that, we have the problem that, for example, you could have a case where part of your wings are torn apart, right, or torn away, and also your propulsion system is not, or is dismantled in this case. And all of this will have implication on your dynamics. And your CBF will not be able to provide safety in this cases anymore, or not guaranteed safety. Maybe whatever happens to your system can happen in a positive direction, such that it will actually help to stay safe, right? But in some cases, it will actually worsen the conditions, and then you have to figure out something to adapt online, right? Or to stay robust. There are like multiple things. You can stay robust. You can adapt off online. You can also use like some sort of like sensor-based approach, like incremental, somehow formulations. Depends on your wishes, your requirements by when you design such systems, right? In this presentation, I just try to look into adaptive control. And for adaptive control, you have two ways of looking into the problem, right? You have direct adaptive control, you have indirect adaptive control. Indirect adaptive control is basically system identification, right? And for system identification, you need persistent excitation or somehow of excitation to the system to learn the parameters and then tune the controller. If you don't have that, you have a problem. For flight systems, you can't provide this all the time, right? So this is not a strong candidate, and also the stability guarantees are weaker. So direct adaptive control is better. Direct adaptive control directly adjusts the gains, right? And by that, you have stronger stability guarantees. And this is helpful. And the problem we looked into is this setting where you have a controller that has to meet some performance requirements and safety requirements, and we applied it to multiple systems. In this case, it's like just an hypersonic light vehicle. In the first step, you just design the direct adaptive controller, which is mostly like just a simple model reference adaptive controller. And I just go through this because I just assume that for most of you, it's very clear. You have this reference model, and the reference model is delivering information of the desired behavior of your closed loop system, right? And then you use this adaptive loss to ensure that if in the case of the system being deviated from your reference dynamics, the gains are adjusted such that you will converge to this behavior, right? And this is the controller that you're using. And for this, you have very straightforward stability guarantees, right? So this is like known for 30 years, maybe 40 years, I don't know. By using Lyapunov analysis, you can derive the stability in the sense of Lyapunov, and under further conditions using Bauerland's lemma, you can actually show that the system is asymptotically stable, right? And if you'll have interested, have a further reading like in this book. It's very nice standard work in adaptive control. Right, so you could argue that if you're stable, you could also somehow have some safety in your system. But again, it's like something very different, right? Because we have stability just means our state is bounded, right? And it's just converging to one point, but it's not necessarily a point that is guaranteeing safety. So we need to use the safety filter, but the questions there is where to place the safety filter, right? And how to guarantee safety during the transient. Maybe we can start with the first question. We have this reference model plant, the adaptive controller, right? You see here. The classical CBF safety filter would place, or at least for the theory, would be placed right there, right? The problem is that for direct adaptive control, the whole knowledge on how to adjust the the system such, the closed loop system such that you will converge in your model or your behavior towards the reference model is here, here, and here. It's in the gains, right? And you're excluding the gains from your safety filter. And the safety filter is using your old model because it's not adjusted. So basically, you're using adaptive control to learn the gains, but at the same time, you're just destroying it again with a safety filter with the wrong model, right? So you can place it like that. And therefore, we said, okay, this was like something we did in 2023. Actually, simple idea. We just say, okay, the only thing we really know is the reference model because this is our desired behavior. We want to be like that. And therefore, we're just using, and again, it's very simple. You see, and this is the reference model, and here, the reference signals, the control input, right? So you just put the safety filter right in front of everything and just act like this is the control input to your system, right? And then you have a reference signal that is safe if you learned the model correctly. And then your adaptive gains are trying to converge towards the safe reference model. The problem here is that the reference model can provide safety when you have the right gains learned. But if you don't, or when you are during the transient, you will have an issue, right? So here again, when you've learned everything, everything is fine. The guarantees hold. So this is not a problem. But during the transient, you will have the issue that there will be a period of time where you're still trying to learn the model, right? And during that period of time, you can't rely on the fact that you're rendering the reference model safe because you are still not at that point to be equal to the reference model, right? So what will happen is something maybe like this, that you will go out and you get back in while your reference model stays inside of it. So if you're lucky, it's tolerable, right? If you're lucky, everything is fine. But in many cases, it's not. And what you can do, it's a very simple approach. You can just tighten your safety set, right? You can just say, okay, hey, if I know, like in a hand wavy way, if I know I have this peak that gets out of my safe set, I'll just place a safety buffer right here and make sure that this peak will happen inside of the safe set, right? And with that, you can stay safe. And for this, it works, right? So you basically just say, okay, hey, if I know I have uncertainties and I have certain influences, I just make sure that I stay inside of a safe subset of S, right? And I'll just stay there. And this works, but it has some downsides. And the downsides are that you will always be conservative, right? So when you have like, let's say this quadcopter and this tries to get to this goal, the easiest way would be to go follow the green line, but when you have the safety buffer, it will try to follow the red line, right? So you always make a detour, you're always being conservative. And we don't need this when we have adaptive control, right? Because there will be a point where we converge, where our adaptive controller provides the same behavior as the reference model, right? And if we have that, the safety filter is valid. And so we came up, or we thought of an idea to make the safety buffer adaptive. And one way was to adjust this was the first shot, right? It works, but it's more like empirically, is to adjust the tuning parameter and the CBF. You have the gamma, which is basically dictating how you're converging exponentially to the with respect to the boundary. And you could find a way to say, okay, hey, I'll use a radial basis function, which is adjusting this gamma based on experienced error, right? And with this, what this will implicitly do is it basically limit yourself to a subset of the safe set based on the error that you're experiencing, right? And when you use adaptive control, this error will converge to zero. And when it converges to zero, you will actually come to a point where you fully exploit the safe set again, right? And the way this is done, it was more empirically. So it was kind of like hard to get theoretical safety guarantees on that. But it was a very good starting point because then we continued working on this and we found actually multiple ways of getting guarantees, right? So one of the collaborators on this was Peter as well as Anu. And Peter took the lead on the idea of error-based safety filters, right? It's basically the same idea, but looked from a different perspective, more from the perspective of interpolation, right? He framed the problem as an interpolation problem between a nominal controller and a worst case controller, and he's adapting based on an experience mismatch. And with that, he was able to get very nice safety guarantees. So if you're interested in that, have a look on this paper. And also we looked into the problem from a point of alternative optimization approach, where in most literature and CBFs, they use quadratic programs, right? And solve it with QP approaches. And if you're using second order cone programs to solve the problem, you can actually find additional degrees of freedom to address the problem in a more general way. And that is what is done there. So by using second order cone programs, you can actually keep a lot of informations without any simplifications and solve the problem. And this is what you've seen here as a result. And it's like just published in LCSS, I think 1 or 2 months ago. So if you're interested in that, have a read. The approach Peter worked on was also validated in a hypersonic case. It just pushed to archive. It's a different paper here. I will highlight it afterwards. But the idea is that EBSF helped to keep the system of the hypersonic glide vehicle safe, in the sense that we have structural and stall load limits. But normally, when you have a hypersonic glide vehicle or reentry vehicle, you have like an aerodynamic corridor in which you have to stay, right? If you are too high, the density is not high enough, right? So you have thin air and you will lose aerodynamic controllability. And if you are too low, then you have the problem that you have a very high Mach number and high density atmospheric layers, and you could experience high heat fluxes, right, and high heat loads. So you have to prevent that as well. So you have this optimal corridor, and we try to somehow come up with an example that is handy but also usable for academic research, in which we can show that with the proposed EBSF, we can ensure that such system can stay in an aerodynamic corridor, even in the presence of uncertainties, right? So here we try to stay in this lane, and we have like an upset event, which is a combination of disturbance and model uncertainties. And after this upset event, a non-adaptive or an adaptive but without an EBSF approach, this will violate the constraint, while our approach was able to prevent safety. Again, I will show the title of the paper afterwards, but it works quite well and it's an interesting result. And if you have questions on that, we can discuss later on. I think I'm bad in time, so I'll have to ramp up fast. Multi-agent systems. Some recent results and work that become interesting because we had some projects in the last years which were great motivation, and of course we had also possibility to work with some great researchers, and that especially also naming Namhoon on that one. The idea is that for multi-agent systems, the way you render the system safe becomes quite complex, because before we just had the issue that the system just needs to look on themselves, right? Let's say I try to render myself currently safe by myself. I don't want to walk too close to the door or to the wall and don't run past, right? But if you all would be here as well, we would have an issue, right? Because my safety now would become dependent on the safety decisions of the others. Right. And this is why multi-agent systems is an interesting field, but also complex. And it started for us with in a project in which we had to design cooperative guidance schemes for missile systems, right? So we had the issue of having many scenarios where all of the missile systems have been, let's say, assumed to be agents that can make decisions, and they have to make the decision between each other who is trying to intercept which target, right? And they have to consider optimality criteria. But at the same time, if you would like to do it online in the real world, you need to make certain simplifications, and you also need to neglect certain dependencies, right? And in that case, they neglected the decision of the others once the allocation was made. What I mean with that is once they knew who's going where, they neglected how the others are reaching their target, right? And by that, you have the issue that they could potentially collide, right? And we took this as a motivation to maybe start finding a approach with CBFs. And we came up with something actually also very simple. So we just said, okay, if we just plug in the standard CBF approach to this, it becomes you get easily to a point where the QPs become very complex and you will lose real-time guarantees, right? Because they start to, if you have, let's say 20, 30 agents, each QP would have to consider 20 or 30 inequality constraints, right? Which is not helpful. So we just framed this as a neighborhood problem. We just said, okay, hey, there is an event-triggered neighborhood, which has some notion of geometry, so distance, but at the same time also some notion of, let's say, criticality in the sense that the zeroed effort miss distance is considered, as well as the direction of the velocity vector. And if you do that, you see you don't need to consider all of them. Basically, just see, even though this is very close, it's not critical because it's flying away. Only this one is flying towards one missile system, right? And this is only considered in the optimization. So from 1, 2, 3, 4, 5, we came down to one equality constraint to be considered. And in the simulation, this worked quite okay. So we have this example where you had like 3-on-3 interception, and all of them have been allocated one target they have to reach, right? And you see at the beginning, the first two have collided because they didn't consider the others and they had no CBF filter, right? There you see it again. And if you add a safety filter, you see the first two there are correcting themselves and trying to fly next to each other until one of them is out of the mission because it's colliding or intercepting. So the other makes the turn. Right? Yeah. And this was just presented at the ACC. Again, it's a simple toy example, but we also looked into it from more complex scenarios, and it seemed to work okay. There are still open questions, especially with respect to latencies and uncertainties in this domain, which we didn't look into that much, to be fair. So it's still open question, but for the simple scenarios, it worked quite okay. Something that caught our interest was for the missile scenarios, you maybe have maybe 20 maximum, maybe 30, I don't know. But never like very large numbers. And for certain UAV, especially when you remember the example I showed you from South Korea, which was tested by the Ministry of Defense, it was like maybe 100, right? Maybe you have 200 UAVs at the same time. So the more UAVs you have, the more agents you have, the more complex the problem becomes, right? Because the dependencies are increasing, and you lose optimality if you don't do it correctly. And one way of reducing dependency and complexity is to use something from actually more, I think, theoretical informatics, to use some task allocation schemes to decompose the events and allocate responsibilities between the agents, right? So basically, we're just saying, okay, not all of the agents have to consider everyone, but some of them are critical for one others. And based on the criticality, we just allocate who's doing what. So this is the rough idea. And that is actually also very much what humans would do, right? When you are in a, let's say in the central station of Seoul or Seoul station, and you have a lot of people walking by next to you, you as a human maybe would always search for somehow consensus to not collide with others, right? Sometimes you see an old woman who's like walking to some direction. You as a human would say, or as a young person would say, okay, I step to the side so she can pass, right? And maybe you are sometimes in a hurry and you're running towards a train and others are seeing you. Maybe they will step to the side so that you can pass, right? And this is the same idea, that you're looking to the problem from the perspective of optimality. You're considering who's having the highest cost to avoid collision, and the lowest cost, let's say, and the one with the lowest cost for a certain event will get the responsibility, while the others are just continue with their mission. And this was done with the auction-based approach. If you try to, or let me go back. So if you do like this and solve it with an auction-based approach, it works quite okay, but it's suboptimal, right? Because the auction-based approach is not optimal in a global setting. And normally we're trying to go for global optimum. Really, we try to search for the real minima and the problem, right? But in the multi-agent setting, it's very difficult to get. Very difficult to get, especially if you do decentralized. So this is like some work we've done recently, and we thought maybe it's helpful to have a benchmark, right? And the benchmark is you have a global allocator that looks onto the problem from a global perspective and allocates and just shares the information of the allocation with the agents, right? Of course, we have the problem here that we have a centralized approach, but it's a good benchmark, right? And based on that, you can always compare other approaches. And this is what is done here. And when you do it like this, you can actually see that you will gain optimality in the sense of mission performance, right? So in this case, I think it was like, don't let me lie, I think maybe 100, but I'm not sure. 100 agents that have been placed randomly at some point here in this area, in this square, and they should try to reach some other random goal somewhere there, right? And it's a messy scenario, and they all are using local QPs for themselves, in which they have to consider everyone, right? And as you can see here, you can ensure safety in this case, but maybe I'll go this way. But you have the problem that you see a lot of noise, right? Because everyone is trying to avoid everyone. So they're trying to fight against each other, and they make decisions based on themselves in an egoistic way. So you have this noise. If you're adding some allocation on top of it, right, and you just make sure that each agent is just doing the collision avoidance that is necessary, the performance goes goes up, right? And you see everyone in this case, after 23 seconds-ish, all of the agents reach the goal. Here it's after 8 seconds, right? So by just coordinating, you can gain performance. And you see it also here. This is the mean barrier value, right? Of the whole swarm. And barrier value means the safety metric, right? And normally you could say the higher the safety metric, the higher the safety of the system. But in our case, we would like to achieve, with respect to mission, right, a low mean barrier value above 1, above 0, because this means we have got a good balance between, or compromise between, performance and safety, right? Because here, you see it in red. This is the MLP and local QP solution, and in blue you have just the local ones. What we see here is that the time series is above the one of the MLP plus local QP. It means the blue one was more conservative, right? And due to the conservatism, we had lower performance, right? So the MLP helped us to be less conservative, but at the same time then gain some performance. And also, you can see here the mean computation time for each of the QPs was also lowered with respect to the idea of just allocating the necessary constraints to the agents. Yeah, way above the time. Sorry. So yeah, this is like the this was the part I try to look into from respect to the design challenges. We still have also the outlook. Currently, I think we've done a lot of like theoretical work on control barrier functions, and maybe it's time to do application work, because there is still the open question of applying the methods into the real world. So we have a hypersonic system, drones, aircrafts, incorporated systems that we're trying to apply or use for our research. And also something that is maybe interesting and not really well researched on is how are control barrier functions transitioning towards civil aviation, right? In civil aviation, you have a lot of questions and certifications with respect to handling qualities, right? You need to meet certain levels of handling qualities. You have performance requirements that you need to be met, for which we yet don't know how CBFs would interact with, right? When you have a pilot in the loop and you have a safety filter in place as well, what will happen to the handling qualities when the safety constraints become active, right? Still open question. And maybe we can investigate this in the simulator, or we have also aircrafts that can be used to do so. Right. So I think I'll skip this conclusion because I am way above the time. Just take away. CBFs are great. You should try to work with them. No, but I'm just kidding. But it's like, like as always for us, each tool has its benefit, right? But there are other tools that provide similar benefits, right? And it's just like a balance. Sometimes it helps, sometimes it's not helping. And me as a researcher who likes the concept, I just try my best to make CBFs or to enable CBFs to be used in many applications as possible, right? And for the ones who are interested, these are very helpful references with respect to the foundations of CBFs, right? It started with Nagumu, and then this is the paper I meant with Frank Algava and his students who came up with the first concepts, and then Aaron Ames, etc. So please have a look. They did really great work. And these are like some of the papers we published in the past and just recently also. So please have a look on that if you're interested. And I think the paper I just meant about the hypersonics is this one, right? It's the last one. So have a look. There is the implementation of CBFs and hypersonic light vehicles explained. And there are also some simulation results. And also just an acknowledgement, all of the stuff is not only done by me, right? I have great collaborators and people, smart people who are willing to work with me. So would like to acknowledge them. We have Peter and Anu from MIT, especially Anu, like introduced me to the topics. I'm very happy to still work with her. Of course, Yu Sang Shen from KAIST, right? Who's, I think, a shared collaborator between us. Of course, I have the pleasure to work with Namun, which would like to thank you again for collaborating, right? It's always a pleasure and makes a lot of fun. And there are also other collaborators, Mark Spiller from DLR, Florian Holzapp and Agnes Steiner from TUM. And also quite recently, Speedos joined the crew in control barrier functions, and I'm happy about that. And yeah, so again, look in their research. For now, you don't need to do it. You have right in front of you, but all of them do really great research and great people. And yeah, thank you for your attention. I'm very sorry that I took a little bit more than expected, right? But if you have questions, happy to answer them.
Thank you.
Yeah. 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 So
if these central use remain.
yeah. I saw like what the difference is between centralized and decentralized. So let's say for the decentralized way, or let's say like that. Maybe we start with centralized because I think this is the most intuitive one, right? So for the centralized way, if you do a centralized, I think the most correct approach to solve the problem would to make a QP or a safety filter that is solving the global problem, right? All of them, all of the agents are included and are solved in one optimization, right? Right. Yeah. The problem is if you do this, you would have to have a central computer, and the central computer would have to provide the control input vector to all of the agents, right? And the problem is you will have latency down the line, and you maybe have also not the possibility to share that much of information with an remotely operating UAV, maybe, right? So you have to make a simplification. So in this case, the simplification was to say, okay, hey, we maybe have this global layer somewhere, but the global layer is not solving the full problem such that it will provide the control inputs to the systems, right? Because it's not applicable. It will just share the decisions, right? And then each of the agent knows which of the agents should be considered or respected, and then they will solve their own local QPs, right? So this is like the thing. And if you do it on a global level, you have some sort of optimality because you can, you know that you can consider all interactions, right? Of course, it's not global, it's not real optimum because the full optimum would need a full nonlinear mixed integer optimization, right? And maybe also a non-linear mixed integer optimization over a finite horizon, because optimality is also not depending on points which are evaluated, but over the time, right? Sometimes you need to sacrifice safety in the one time step to have maybe optimality or better solution the next time step, right? So the problem itself is quite complex. But in this case, it's a first good shoot. It's a more or less okay benchmark. If you go for the auction-based approach, the problem here is then trying to look in this from a different perspective. Here, you would say, okay, if I don't have the ability to have some central computer instance somewhere, the UAVs shouldn't be able to do everything by their own, right? And if they do everything by their own, they need to find a way to figuring out who's doing what. Here, the approach was to use an auction-based approach, actually a greedy auction-based approach. And by greedy, I just mean there are no consensus seeking. Let's say there are not multiple consensus rounds. You just have one round in a certain neighborhood where you have a list of events, and the one agent that has the lowest bid gets the event. Normally, you will have like in some auction-based approaches, you would have consensus rounds where you reevaluate the decisions and go over it again, right? You don't do this here. This is a very simple approach. It's greedy, but doing so, you will lose optimality, right? But you gain, let's say, speed, right? You will converge fast. You will make decisions fast, and I think this is also a very interesting field of research. I think people with interest in task allocation and consensus seeking algorithms could actually improve this quite fast. But I think this is just the first shot, and there should be someone interested in this field to maybe find better approaches, right? I hope I was able to address your question. Yeah. Okay. Oh, thank you. I'm happy about that. Yeah.
Awesome.
Yeah. 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 I'll just try. So yeah, basically just rendering the reference filter, the reference model same. Yeah.
That's good.
Yes. Yeah. 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 Under certain conditions. Yeah. 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 It's a good question. So this was actually the one that was driving the research. As you said, so this is like you can do it like this, right? Straightforward. And just basically have a certified reference signal that is safe, right? But it's only certified safe if, as you said correctly, you've learned the model, right? During the transient, those guarantees are gone. And there are like two ways of actually obtaining guarantees, right? So one way is to add this buffer, right? This delta. So this delta here is basically it's very, very simple actually, right? So you're just saying, okay, I know the maximum mismatch and safety I could get through uncertainties, right? And I just place a safety buffer with this size onto into my subset, and I just constrain the system into this, right? And then you are operating in a subset, and then you're good to go, but you're conservative, right? And with adaptive control, we know we only need this buffer during the transient. And once we've learned the adaptive stuff for the model, we're good to go. So I started with this, and it's just like it works empirically fine, but yeah, no theoretical guarantees. But there are like other ways. So these two approaches provide theoretical guarantees also during the transient, right? So what they basically just do is, so actually in both cases, Lipschitz bounds are avoided, right? Because you have a they have continuous dynamics, right? Which are somehow bounded in the way they evolve, let's say, over time. You can exploit this knowledge to find time varying buffers that provide safety guarantees, right? So yeah, good question. Again, I think if you're interested in this field, have a look. Actually, there is also, I think, a lot of space for research because you have to make certain assumptions and simplifications to come up with certain things, right? And there's a lot of knowledge that needs to be given beforehand. For example, you need to know the bounds on the uncertainties, right? And the parameter offsets or mismatches. And therefore they need to be bounded. And there are also other things you need to learn. You need to have to be known a priori. And maybe there are ways to relax those requirements on informations and find more general approaches, right? Another way is also another problem is, at least for this approach, you use a second order comp program, right? It's kind of like slightly more general because you don't need that much information, but the cost is that you will have more complex computation, right? And maybe there is a way of finding also simpler approaches to that. Yeah, yeah. Hopefully, I was able to answer your question. Yeah. Yeah. So yeah. So actually, the idea is for doing this, right? The idea is that you're saying, okay, I know I will have, if I have a mismatch and I didn't learn the model, I will have a like barrier function error, right? So this is just the mismatch in safety, right? Between the reference model and the actual model. And we know from adaptive control that the error is bounded, right? EX is bounded, it needs to be bounded. And when EX is bounded and there's Lipschitz by a Lipschitz continuity you will also see that EH, this EH, can be interpreted as a function of EX, right? And we know EX is bounded, we know EH is bounded, and this bound is capital E, right? And you can get it in these simulations. And if you know that we need to make sure that H needs to be greater or equal to 0, right? This is the condition for safety. You can actually construct the case or the condition that needs to be obtained in order to ensure safety for your system, right? And if you do this, you can easily get this buffer that is needed. It's very straightforward. It's actually pretty simple. And then you get this, right? The only thing that is sometimes kind of like manual is to obtain this, right? Because you would, when I did it, I had to do like some Monte Carlo simulations, right? To do all the parameter variations to see what is the worst case deviation that I could obtain, right? But maybe there are also analytical ways. I don't think so. But maybe it's an inspiration, right? So I think there's a lot of stuff that can be used to make this simpler. Yeah. Yeah. Okay. Thank you for the question. Please. Yeah. Mhm. This.
Like you said, yeah. What it places the same exact column.
Sorry, the same exact copy of.
Same.
Yeah.
That's the reference photo. We claim that's a reference.
Mhm.
But actually, that is a whatever. So it would be the first, not just
Yeah.
Maybe. This.
It's interesting. The only thing I'm questioning myself is that we could have the issue of wind up, right? It has to be addressed because then if we place it here, you will still have the problem that the reference model will try to converge the system towards R, right? R is still driving the reference model, then we have XM, and E is used for the adaptive flow. So we will have the safety filter here. This means the safety filter, even though it would use the right gains or the adaptive gains, would try to adjust the closed loop system in its behavior, which maybe leads to the problem that we are deviating from XM on purpose, right? I think it's possible. It's interesting. The only thing is you would have to, or the only thing that is needed is somehow a way of using or trying to make sure that E is corrected somehow, right? Or the state of XM is somehow correct. But I think it could work. Yes. Yeah. Yeah. Also, me not. Yeah. Yeah. Sorry. Yeah. 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 So you would place safety filters on both levels? Yeah.
reference levels.
Yeah.
But if we focus on and we want for water station, then I will also to the reference. In that case,
wait, if I understood correctly, please correct me if I'm wrong. Or so you would put the safety filter there, and then you would use somehow like a closed loop reference model in here where the mismatch is actively considered in order to make sure that the reference model is converging towards the desired state.
so if we just put the reference,
Yeah.
safety. If we stop when the constraint is that there is but because of the structure we look up to still it is good. I haven't checked what
Yeah, I'm just asking myself, the only thing is I see your point. I think it could make sense. It could make sense. I'm just questioning myself if if there is something missing with respect to how the reference model is evolving and how the error is evolving, right? But maybe I have to see it or not. Then it makes maybe sense. But it's an interesting question. If you like, we can talk about it. Yeah.
wrap up.
Yeah. But thank you for your time.
Session.
Yeah.
Thank you very much. Thank you very much. Honest. Thank you.
Well, thank you, Namun, for being invited.
Yeah. Hopefully, if we get our